Hi, everybody. Welcome to our next round of IRIS-HEP Fellows Talks. Up first is Giedrius.
Hello everyone, my name is Giedrius and I will present my fellowship project in IRIS-HEP called Adding a RNtuple to the Analysis Grand Challenge. I would like to start with the bigger picture to understand the value of this project. The High Luminosity Large Hadron Collider is a project which aims to crank up the performance of the LHC in order to increase the potential for discoveries after 2029. The main objective of HL-LHC is to increase the integrated luminosity by a factor of 10 beyond the LHC's design value. In simple terms, the higher luminosity we have, the more data the experiments can gather to allow them to observe rare processes. But this brings a new problem. Analysis workflows commonly used at the LHC experiments do not scale well to the requirements of HL-LHC because more data means more computing power is needed. And there's going to be much more data. To address this challenge, the IRIS-HEP Software Institute started the Analysis Grand Challenge, shortly AGC, project to optimize the data pipeline. AGC is about performing the last steps in an analysis pipeline at scale to test workflows envisioned for the HL-LHC. This includes things like columnar data extraction from large data sets, processing of that data into histograms, statistical model construction, and statistical inference, relevant visualizations for these steps. All this must be done in a reproducible and preservable way that can scale well to HL-LHC requirements. The scope of my task is only a smart part of the whole AGC. It mostly includes columnar data extraction from large data sets. And to do that, three main tools were used: Uproot, Awkward Array, and Coffee. In Large Hadron Collider, particles are accelerated and they collide near the detectors. In this example, the CMS detector. CMS detector is triggered and event data eventually, after analysis and validation, is saved long-term into columnar data storage in a root data format. Now, to read these files, root files, there are a lot of different ways. One of them is using roots interface. Another one is using uproot, which is using purely Python. And there's another way using Coffee, which is even higher abstraction level, which uses uproot and dask for distributed computation. And there's much more, which I'm not going to get into now. What I want to talk about is the format, which is the format used in root. For 25 years and more, columnar data was structured in T3 format, and RNtuple is a redesigned input-output subsystem aiming to reduce disk and CPU usage for the same data content and be supported by modern hardware with built-in support for multi-threading and asynchronous input-output. There's much more, but I'm not going to get into it today. The criteria of my task is making sure that uproot and Kafir workflows support RNtuple data files without errors. I was blocked in the Kafir approach. I will talk about it later. The other point is, after comparing T3 and converted RNtuple files, data should not be corrupted. It should be identical. The third one, RNtuple workflow performance should be compared to T3, and finally found issues should be documented for the team. These are some technical steps I took during my fellowship. Firstly, I started with already existing Jupyter Notebook workflow in GitHub, which works well with T3. Then I changed T3 files to RNtuple files to use the same workflow on. Then I set up loading files using two different approaches, uproot and Kofia. Uproot is much more simpler and it has lower abstraction level, while Kofia is more complicated and it uses distributed computing and much more. And eventually I was blocked in a Kofia approach because Dask is not yet supported by Uproot's RNtuple interface. And Dask is responsible mainly for distributed computing. Then we created our own RNtuple files with root instead of using pre-existing ones, which were given. And main focus from then was put on uproot approach. Multiple problems related to RNtuple were found. Time was spent debugging, documenting, and solving these problems in uproot repository. Finally, after solving critical bugs and ensuring data integrity, multiple tests were created to compare the operation performance between T3 and RNtuple files while using uproot. Here are some tools used which helped me a lot. Firstly, it was Kofia Casa server, which helped me use external resources. I didn't have to use my own computer resources. There were computer clusters for that. And it also helped a lot while trying to make Dask working because Dask needs clusters of computers and I need to use remote servers for that. Then Jupyter Notebooks helped me to easily manage and share code. Kofia, Awkward Array, and Uproot were mainly used to load root data and analyze it. I used visualizing tools to debug because it was necessary to see the bigger picture with visuals. I'll show it later. And also we had to create our own RNtuple files because pre-existing ones caused some problems. We used LX Plus server for that and root converters. Git and GitHub help to manage different versions of code and eventually contribute, merge new code into the mains. And GitHub just helped a lot to sharing simple code snippets with colleagues. Here are some error analysis examples. On the left, you can see a graph which shows match results. One indicating that record for T3 and RNtuple match, and 0 means that they don't match, while blue indicates the transition from one point to the other. The main point of this picture is me trying to say that it was necessary to use visual tools to finally understand where the issue was. It became clear that the issue was related to clusters, and in this picture there are 7 clusters, and from this moment I could finally start on working how to solve issue. A different analysis example shows that to understand what went wrong, I had to analyze files and compare them byte by byte. From this point, after comparison, it was clear what went wrong, and then we could create an issue for that in GitHub. During the fellowship, in uproot RNtuple object, multiple issues were found. I specify them here. One of them was while using Kofia, RNtuple object was missing some keys arguments. It was a simple fix. We solved it. The biggest blocker was Dask is not supported by RNtuple interface yet. I couldn't continue this, so I focused on uproot. RNtuple object has no attribute, no entries. This was already solved by other developer in the draft PR. I just had to test this PR. Data integrity was lost when loading arrays from multiple clusters. That's a mistake here. this was solved, and this took the most time, and it felt like it was an important solve. And the last one, uproot file loading, fails when using RNtuple. File created with recent master root. An issue in GitHub was created for this problem. Eventually, performance tests were done after data integrity was ensured. I created a notebook for that, for all these tests, and here are the results. On the table, we can see that RNtuple is highly efficient in most of the operations, except one, which is not recommended to use because it is slow. So it should be fixed as a bug, should be analyzed why it's happening, or it should be hidden from the end user so it doesn't use this way to load files. Then data showed one interesting thing, that D3 is much more slower when we are loading all arrays, but it is almost the same when loading one array. So I decided to load increasingly more, increasing counts of arrays, and see and graph the performance. So it's very clearly visible in the graph on the right that RNtuple with more and more data doesn't grow as the execution time of it doesn't grow as fast as T3. And the conclusion of that for this would be that it's much more worth it to use RNtuple when loading big amounts of data, a lot of arrays. And finally, I will pinpoint some potential next steps that could be done from my perspective on this project. So firstly, RNtuple's data integrity must be ensured with each new root release, because each new release might create different RNtuple files, and uproot might not be able to read those files. Therefore, this integrity must be ensured with each version. The second point is the support of Dask and Coffee is required to distribute computation across computer clusters when using RNtuple. That's the blocker I had, and it needs to be developed. The third point would be performance testing should be done in Dask Coffee scope when using RNtuple. What I mean specifically is when the Dask and Coffee is supported, then tests need to be created to measure the performance in the scope of these tools, because it's higher abstraction level, it's distribution systems, and there might be different bottlenecks than different than in uproot. And the fourth point is the use cases of physics analysis should be examined to create additional performance tests within the scope of uproot, the one I was working on. But my guess is these tests is not, there could be more tests than I created, because I don't know what type of use cases physicists might use, or what type of use cases Coffee might use. Therefore, this needs to be analyzed further, and tests should be updated. And thank you for your attention. It's time for your questions.
Thank you, Giedrius. We have a couple of questions. Vangelis, I think you had your hand raised first.
Yes, thank you. Thank you for this presentation. A couple of things I want to ask is if these updates that these issues that you sorted in uproot, if this has been released, so if I pull the latest uproot, will it has, I don't know, these issues found on your slide 8?
Good question. No, if you install uproot version with pip, you will not get these fixes. What you have to do is use the main version in the repository. I checked this exact thing you are asking right now after it was merged, and I saw that the version in pip was the same. Therefore, if you want to have these changes, you would have to use main branch in the uproot repository. Unless
Okay.
there's something I misunderstand. Yeah.
I guess it will be released. I see now, I see now that the latest in PIP is the latest tag that it's on the repository of Uproot. So I guess on the next release, then this will be there after 5.3.12. The next one should have them. This is at least what I understand the development workflow is.
Correct. I think
okay.
at 12 it will be present.
And then second, you're trying to put an AGC together. So I'm wondering if there is a notebook somewhere where we can feed with RNtuple files and run it. Is this one that you point out?
I think you could run my tests with this notebook. I can open it. And what you could do is to run my written tests in here with any RNtuple file. But of course, there's much more you could do. The other thing is the RNtuple file must be proper. What I mean is when RNtuple is created with the most recent master version of root, there are issues. It doesn't work. It breaks because there are bugs unsolved.
I see.
It only starts with certain versions. So there are a lot of ifs, but yeah, you could run a RNtuple file with this, and if it does all the tests, well, not all of them, because there's T3 comparison. You would have to compare T3 and RNtuple.
Yeah.
But you could try, yes.
All right. So even from the root side, this is not completely fixed things yet, right? As you say, the master branch of root is not gonna give you a good RNtuple file yet.
Good RNtuple file, we should ask what good RNtuple file means, because in this context, bad RNtuple file is the one who cannot be read by Uproot. The bad RNtuple file in this context is the one which loses data integrity while read by Uproot. But I'm not saying that root cannot read this bad file in the context. Maybe root is able to read it without issues.
I see. Okay. Thank you. Thank you for looking into that.
Which is to say, RNtuple's schema is not yet frozen. And I guess that happens in 6 months or something like that.
Schema is not what? I misheard the word.
Frozen, meaning it's going to continue changing for a while in incompatible ways. So it's sort of expected, but it means that Uproot now has to, for the moment, has to chase changes as they come. And yeah, we found one of them along the way.
Yes, I think yes, it's not frozen for sure because we just witnessed it changing it, and once it's frozen, it should be also documented well and available for everyone for easy access. I think, especially for Uproot developers too, since they can update the Uproot code to match the frozen schema of the RNtuple.
All right, Alex, you had your hand raised?
Yeah, thanks a lot for the talk. I was wondering, in this table where you have these performance results on slide number 9, you show one entry which is sort of loading the file. Am I understanding correctly that this is effectively the metadata reading that happens if you just open the file, and that has gotten so much faster now? Is that correct?
Could you specify which loading are you talking about specifically?
The one you call load file, which is 0.001 seconds for RNtuple and like 0.3 seconds for T3.
That's a good question. I didn't look into it, what loading events mean, but loading events, I cannot answer if it's loading metadata or not, but it's loading events like this. You can show you with an example. So I can show you the test. I'm sorry.
Ah, so okay, so it actually does open the file. Okay.
So load file is this function, and I cannot answer it specifically. I can show you with the code what does it mean.
Okay, I guess we also have Jim here who would know if somehow this does something different, but it does read metadata still with IRIS-HEP, I assume, right, Jim?
Sure, yeah. So you read metadata to find out where the objects are in the file. So for RNtuple and T-tree, the initial metadata of the T file and T directories and all that, that's all the same until you get to the T-tree metadata object or the RNtuple metadata object, which are different. But they are both metadata, and they're both interpreted in slow Python, using the struct module. And it's only when you get to the point of knowing where the buffers of numerical data are and just read those out that actually gets fast. I'm looking at this code here with the load file with uproot open as F, and you get the events T-tree. I don't know how this could work because when you leave this bit of code, you've left the with statement. The file is closed, and so you can't read from the T-tree after that.
But its events are saved into a variable.
So, but events is the T-tree metadata or the RNtuple metadata. It's not the arrays. I don't see any function call to dot array or dot arrays or dot iterate or any of those function calls that actually read data as opposed to metadata.
I see. So I actually was able afterwards to load arrays. So
that's weird. Okay. Yeah, because the with block is supposed to close the file at the end of that with block.
So either the file is not closed, or this might be not the metadata based on this.
It's the
or
metadata.
Else? Okay, it's metadata.
Yeah.
I don't know the answer. I don't know why it works as not expected, but
Yeah.
it did work for me.
Yeah, I'll have to try an example of that. Because that would be a file leak.
Yeah, it's worth looking into it.
File handle leak. Leaving files open that should be closed. But okay. Anyway, yes, that's if you're doing performance tests, you want to either cleanly distinguish between the time spent reading the metadata and getting all ready to read the arrays, and the time spent reading the arrays, or work with such large arrays that it completely dwarfs the metadata reading anyway, which depends on the size of the arrays. If the arrays are large enough, then the reading time will be dominated by them. So the time spent reading the metadata will be insignificant. What's the horizontal axis? Count of loaded arrays. Is it number of arrays or number of elements in the arrays?
Could you repeat the question?
Count of loaded arrays, is that the number of arrays or the number of elements in the array? So are they the size of the arrays?
Number of arrays, because
Okay,
one
so
array means just loading one key, like electron ETA. So that's one array. Then
okay.
if we load electron ETA and electron PT, that's two arrays already.
Okay. Yeah, because that jump, maybe you're switching from small arrays to big arrays.
Could be, yes.
If they come in some order.
Yes, if we change the order of key names right now, just the keys and went one by one, we might find the answer if that's the case.
Yeah. Or with that one bump there, it could be just one really big array, like it's Gen particles. Could be Gen particles. And then,
And
Gen particles.
and
Yeah.
after loading that array, all the other array loadings get slower too?
No, but all the ones after would have to be something. Like suppose that the first ones are all triggers. Those are arrays of Booleans. They are not nested. They should be super fast.
Yeah.
And then, I don't know, I'm just making stuff up. But then you get the gen particles, that's the one slow one, so you get a big step function there. And then after that are all of the nested data that are bigger and more complex than Booleans, and so then the array will be different. But then, why don't you see that for the RNtuple? Because exactly the same thing should happen there. There is a step in the RNtuple. It happens at the same place, so just below 200. Same place as a corresponding step in T-tree. But
Yeah.
then this isn't a course, the next big jump and then the higher rate thereafter doesn't happen for the RNtuple.
Well,
But,
the perfect test for that would be do each array increment by 1. I incremented by 50 because it took a really long time. But by 1, we could see each bump and peak, and we could compare arrays. Also, yeah, good point to change the order and see which one is loading faster or slower.
Yeah, I'm just saying that there's big arrays and there's small arrays. If you don't want to use, you could use synthetic data, like not physics data, but just some made up data in order to control it, so that you can do these studies as a function of how complex the arrays are. Or if you want to do this for a realistic physics case, you could randomize the order of the arrays.
Yes, that's a good.
That would just sort of mix them all up, so that you would have typical array sizes and complexities, but your plot wouldn't have these structures from the fact that there are a few quantitatively different types.
Thank you, Jim.
All right. Thank you. It seems to have brought up some questions and some further discussion, so that's always good. Thank you, Giedrius. Next up is Sara. Sara, you want to go ahead and share your screen?
My name is Sara, and my project is charged particles reconstruction at the Muon collider. My mentors are Dr. Griso and Dr. Rastogi. So the current colliders are able to reach the proposed Muon collider would be able to reach a fundamental center of mass energy about a factor of 10 higher than is currently possible, and it is a high priority for the field. And this can be achieved by building a Muon collider. Muons are particles which are unstable and decay into an electron or positron, accompanied by neutrino and antineutrino. This is a picture of the proposed Muon collider. So muons are unstable, and after they decay, they tend to scatter in all directions. Some will enter the detector and cause noise by colliding with the tracking detector. Every square centimeter of the active area of the tracker detector is hit hundreds of times. A muon collider detector faces the challenge of separating the products of muon collisions from an intense beam-induced background comprising of secondary and tertiary interactions of muon decay products. So this is a picture of the muon collider detector. The innermost region shown in yellow represents the tracking detectors. The tracking detector consists of a full silicon detector divided into 3 sub-detectors: the vertex detector, the inner detector, and the outer tracker. It has shielding nozzles made out of tungsten, and the nozzles are covered with borated polyethylene in the forward regions along the beam axis. This is to help mitigate the beam-induced background by trapping particles generated by the decay. So this table shows the specification of the 3 subdetectors. So we performed realistic digitization and simple digitization for the tracking detectors. Simplified digitization is used for initial studies and feasibility assessments. Hits are generated by smearing the simulated truth level positions based on a Gaussian template of the position resolution. Realistic digitization is used for detailed design and performance optimization. It incorporates comprehensive models that simulate the full complexity of the collider environment, including beam-induced backgrounds, detector responses, and material interactions. Realistic digitization for silicon detectors includes detailed modeling of sensor thickness and the response of front-end electronics. So we can look at the pixel hits using realistic digitization, and these are the figures showing hit multiplicity and cluster multiplicity. So in the Muon collider, when particles interact with the detector material, clusters are formed and a series of hits is produced which are grouped together. These hits can be from signal particles such as from the Muon gun or from the background particles like BIP particles. The length and characteristics of clusters such as the hit length and multiplicity can help distinguish between different types of particles and interactions. The BIP produces longer clusters because there are many particles with lower energies. This is a figure which shows that the further you go from the interaction point, the angle formed reduces, whereas closer to the interaction point, you have a bigger angle. Correlation between the incidence angle and the number of pixel hits is used to differentiate between signal and BIP clusters. This helps in rejecting long clusters that are typical of BIP particles. For each cluster, we found that the BIP particles had more hits compared to the Muon signal gun. This can be seen by the plot on the right, which shows the number of clusters versus the number of hits per cluster. And BIP particles form more clusters at very small and very large angles of incidence compared to particles from the Muon signal gun. This can be seen from the plot on the left. The red line shows the plot without BIP, and the blue line shows the particles with BIP. Now let's look at cluster shape analysis. The purpose of the cluster shape analysis is to reduce the readout rate from the tracker detector, which also improves the run time. CPU consumption is reduced and the performance of track reconstruction algorithm is enhanced, which leads to higher efficiency and lower false positive rates. These plots show that BIP particles produce a lot more clusters than signal for the same energy range of energy deposited. In both of these plots, the red curves show BIP. The red curve without BIP shows discrete peaks that decrease as the energy level increases, and the blue curve with BIP is a smoother curve with more consistent energy levels across energy ranges. The plot on the top shows the vertical barrel detector, and the one on the bottom shows vertical end cap detector. currently, there isn't much separation between muon gun signals and WIP collision events with thin sensors. There are plans to increase sensor thickness to study the effect of on the size of clusters when WIB is present and absent. And there are plans to improve cluster-shaped filters and make them better at WIB rejection. There are also plans to optimize the time window selection for out of time WIB rejection. And there are plans to study the impact of increasing front-end threshold on the pixel hit multiplicity and cluster energy with the optimum sensor thickness and time window. These are the references. Thanks to Dr. Griso and Dr. Rastogi for their valuable mentorship throughout the course of this program, and thanks to IRIS-HEP for funding my research. Any questions?
Thank you, Sara. Any questions for Sara? Okay, thanks again. Samuel, you're up next.
All right. Hi, everybody. I'm here to talk to you about charge particle reconstruction on Muon collider as well. This is my project this summer with Simone Pagangriso and Rocky Balagarg. And I'm Sam Ferraro. I'm an undergrad at Brown. So before I get started, I have the obligatory Muon colliders are awesome slide here. So last year, the P5 report, which is the steering committee for particle physics in the US, suggested that a Muon collider would be one of the best options to push the energy frontier, especially here in the US. And there are lots of reasons for that, but some of the main ones are some of the fundamental properties of muons. As elementary particles, when they collide, all of their energy goes into the collision instead of when you have protons colliding, you have parton distribution functions and the quarks colliding with fractions of energy. In addition to that, they're higher mass than electrons, about 200 times more massive, which means you deal with a lot less synchrotron radiation as you get up to these higher energies. And that gets you to this sort of graph here that shows you with a 14 tera-electron volt muon collider, you probe the same physics regime as 100 TeV proton-proton collider, which is a pretty decent number. In addition to that, the fundamental properties of the muons, high-energy muon collisions create a lot of effective vector bosons, which are very sensitive to the Higgs. So at a high luminosity muon collider like is being proposed, you have a lot of sensitivity to the Higgs boson. You can get a lot of stronger constraints on the parameters around it, which is important for current particle physics. So in general, this is like a good future collider. My work this summer is broken down into two projects with the Muon collider. The first being the testing and validation of the new ACTS version. So ACTS, or a common tracking software, is the tracking library that was chosen to be used for the Muon collider. Track reconstruction, just to give you an idea, is the process of taking all the hits that hit the innermost detector of one of these particle colliders, either CMS or ATLAS or a proposed Muon collider, and building up the tracks that particles took through it. So seeing it, there are a bunch of hits, and maybe this hit, and this hit all go together as part of a track of a particle going through with a certain amount of energy. So the software development team, before I got there, transitioned from using ACTS version 13 to using ACTS version 32, which is a pretty big step. In addition to that, the algorithms were improved and the interface was changed. So my job was to validate this new version, make sure that it's consistent with the old version, performs either the same or better than the old version, and make sure we're not making a mistake by switching to it. So I ran a bunch of simulations, and here are some graphs from them, but basically they show that the efficiency remained the same, which is like its ability to reconstruct the tracks, and the fake rate remained the same, which is its tendency to generate fake particles out of nothing. So that's great. That means that the new version is equivalent to the old version in terms of performance. In addition to that, the new version was significantly faster, which I'll explain in a few minutes is really important for the Muon collider, but this is a great sign. So the new version that implements the newer ACTS has been packaged in a new container and is now on CVMFS. You can find it there if you want to use it and try things out with the Muon collider stack. So my second project was taking those tracking processors and converting them to Kiefer-HEP. So the reason why we need to convert them is because of the beam-induced background at the Muon collider. So the beam-induced background, which Sara talked about a little bit, is this background of particles that comes from muons being unstable. They decay, and then their decay products intersect the detector, and you can see from this simulation of the bib, you get a really high multiplicity of particles, especially the low momentum particles intersecting your detector, which is a problem for reconstruction, because in the end, reconstruction is a combinatorics problem. The more particles you have, the longer it's going to take. So the bib takes what used to be on the order of seconds to something that's on the order of minutes to hours, which is a problem when you have a lot of events coming in from a high luminosity collider like the Muon collider. So we need faster reconstruction, and the solution to that is multi-threading. The current Marlin framework that the processors are built in does not allow for multi-threading. It's not thread safe, and so that's not feasible there. That framework is the ILC soft framework. It uses Marlin, and it uses LCIO as like the input-output for data, and it's well developed, well documented online, but you can't parallelize. There's this newer Kiefer-HEP software framework that replaces Marlin with Gaudi and LCIO with EDM for HEP. It's still being developed, and there's not a ton of documentation online for it. There's some, but not a ton. But the natural parallelizability of it makes it really enticing for this project. So my job was to take all those Marlin processors and convert them to Gaudi functionals, make sure all the LCIO tasks are being handled by EDM for HEP, and convert the steering files. So as a whole, this was over 4,000 lines of code between the two packages I was working with. One was ACTS tracking, which was the actual implementation of ACTS, and TrackPerf, which was just a collection of smaller algorithms used to analyze the performance of the reconstruction and make sure it was doing what we wanted it to do. That was over 8,000 additions and deletions, and with that many changes, of course, comes along lots of runtime and compile time errors that were compounded by the sort of dearth of documentation online for Gaudi and EDM for HEP. But eventually, after working through all those errors, I got the algorithms to run all the way through and obtained results. So the results look pretty similar to my first project. I'm comparing two different reconstruction algorithms in terms of their efficiencies in both ADA and PT and their fake rates. And as you can see, just like the first project, they perform pretty equivalently. We'd expect them to be almost exactly the same because we haven't changed the algorithm at all. We've just changed the framework they're built in. There are a few differences, which I'll get into on the next slide, but all in all, you can see the efficiency is equivalent and the fake rates are equivalent as well, which means the Gaudi reconstruction algorithms work just as well as the Marlin, which is what we were going for. There are a few remaining issues. Kiefer-HEP and EDM for HEP especially are still in development, and there are aspects of them that will change. EDM for HEP is still in pre-release right now, which means there are a few bugs, and I had to implement workarounds for those bugs. In the code, I left the proper way to actually implement them, commented out, as well as the workaround. So as soon as EDM for HEP goes into full release, fixing those bugs, it'd be easy to go back into the code, remove the workarounds, and implement the proper way to do things. But in addition, as a framework changes, the code will have to be updated to reflect that. This is true in any software framework you work in, whether it be Kiefer-HEP, ILC Soft, or something else. But these changes will tend to be minor in compared to the conversion process as a whole. So it makes sense to start converting our algorithms now, not just the tracking, but all the algorithms for the entire stack. As for next steps, of course, is parallelization. That's why I did this conversion process in the first place. We'll start with within event parallelization, taking the seed finding and reconstruction steps that take a lot of time and parallelizing those. A few changes left to be made, but in the end, it should be doable to do that, making the event processing time significantly faster. And as Kiefer-HEP develops, it should become possible to multi-thread over events, meaning that in the end, we should get something that looks similar to this cartoon where you have multiple events running at the same time, all multi-threaded to run significantly faster than before. So my Gaudi transitioned algorithms are in a draft pull request to the main Muon Collider software stack, and I've begun work in this multi-threading direction in a separate branch. In addition to all the work I've done this summer, I've also gotten the opportunity to share my work. I'm, of course, sharing it with you all now, but I also presented a poster of my work at the US Muon Collider Collaboration Workshop at Fermilab. and to the International Muon Collider collaboration. And Simone presented my work to the Key4HEP software development team. So this summer, I've gotten a lot of opportunity to learn about coding and the hard skills of particle physics, but also the softer skills of communicating my work to others and what the particle physics community is like in general. So it's been an amazing experience, and I want to thank the IRIS-HEP fellowship team for giving me this opportunity, and also to Simone and Rocky for guiding me through this summer. So thank you. Does anyone have any questions?
Nice talk, Sam. Any questions for Sam? We're always happy to hear that you had a positive experience in our program. So, and thanks again. Next up, Dennis.
Okay, so hello, my name is Denis, and today I want to present a result of my IRIS-HEP project for this summer, and with the topic of analysis grand challenge with Atlas PHYSLITE data. A little bit of outline. First of all, a few words about analysis grand challenge. It was already introduced today, so I think we don't have to spend much time on that. After that, a few words about new file format, which is PHYSLITE, and after that, step by step moving with how IGC is implemented, and after that, some conclusions and the final results. Just a few words about analysis grand challenge. It's kind of benchmark to make sure that everything work correctly. I mean, there is several different libraries, and at least this AGC, it's to bring it together and to check that it works as it should. And of course, on some data analysis, which can be, which can serve as an example for all the researchers who want to do their data analysis. And this particular one is testing input-output of the PHYSLITE data format, and a bit of steps which implemented here is first of all we start with columnar data. After that we move to the we take this data in our code, do some event selections like usual in data analysis for high energy physics. And after that, we build it in histograms, look at some distribution, and the next step is to build statistical model and make statistical analysis to estimate uncertainties. And after that, having final result, let's say, and we can do some diagnostics with that result. And the key point is that all of this must be renewable, and it must be possibility to change something and so on. So what about data? The actual data, it's one that was released this summer from the ATLAS collaboration, and this data, what ATLAS collaboration released, it's physically measured data from 2015 and 2016, and it's really large amount of data, and all of that stored in PHYSLITE data format. And now as it is open, this data is openly published. One maybe want to do analysis on the data, and one more things of this analysis grand challenge of mine is that it can be like an example for some guy how to do that analysis. And also this physically measured data came together with Monte Carlo simulated data, which also needed for analysis. And to be honest, in my work, I analyze this Monte Carlo data, but it completely the same can be done for the real data. And the data can be accessed with this link or with this link. And a little bit about PhysLite data format is that this the reason why we need this new data format is because we want to optimize disk hard drive space taken by events in high energy physics. Of course, it's all in favor of high luminosity upgrade of an LHC. So how do we actually read our data? We have nice tools, which is Coffee, a columnar object framework for effective analysis. Already today was introduced, but okay. And this Python package, which is Coffee, contain PhysLite schema, which some piece of software which can translate data from the file to our load it into memory in form of output array, and here is just a piece of code to show how easily the data is accessed. And at the end, it returns events, which is output array. It contains a field with some properties of events. And now about what kind of data analysis we're doing. It's just an example. Of course, project is not about data analysis, so we try to keep it simple. Let's say what we have from the LHC. Two proton beam colliding, they created, let's say, top quark. That quark decayed, and product of that decay we measured in detector. The raw detector measurements do through event reconstruction, and in this PhysLite data already reconstructed events is stored. So we can just apply some cuts on some variables of that of particles which was detected, and in this way do some event selection. And what actually we do, it's first of all, we look only at event which contain exactly one charged lepton, and at least 4 jets. Jets, it's what remained at the end from the quark after hadronization. Also, we have some preselections for lepton and for quarks on transverse momentum and pseudo-rapidity. And actually, what variable we want to analyze, distribution at which we want to have a look, it's in our case, it's 3-jet mass. It's basically invariant mass of 3 particle jets and so-called HT. And for now, analysis for both of them slightly different. For 3-jet mass, we have additional requirements that we select only those events which have at least 2 bit-tagged jet. Bit-tagged is let's say jet which recognize like most likely to be jets with B quark. After selecting this event, we have, let's say, at least 4 events, 4 jets in each event. We combined from that jets all possible groups of 3. After that, pick one group which has the largest B-tag variable, there is variable which is floating point corresponding to B-tag, and so-called discriminant. And we pick one one group of three quarks with larger discriminant and just calculate invariant mass of that three particles. Okay, here is our so-called three-jet mass. The second, what we look at, it's so-called HT. It's additional requirement for event that we must have only, not only, but exactly one. Jets which be tagged, and after that, for each of such events, we calculate scalar sum of transverse momentums, and okay, here it is our HT variable. And very nice tools about coffee that it is provide us possibility to do that in parallel. One just need to write a function, what steps of analysis must be done, and just with very nice functionality of coffee, it can be easily parallelized so that our work distributed in chunks of works which calculated parallel in parallel way in a cluster, and it is much faster. And additional, our input data comes not in a single file but in rather multiple small size files. So it is already possibility of do it in parallel. At the end, the data automatically merged into final histograms, and we just can have that final histograms. And in my analysis, I used this cluster, Coffee Open Data, which if I don't mistaken, it's a Nebraska University cluster, and it already contains all that library pre-installed. And here is how does the final histograms look like. Okay, this one for three-jet mass, this one for HT variables. And as I mentioned, we use Monte Carlo data, so we know how this data was generated, and we know what physical process was involved into creation of that T quark. And here even the distribution by this physical process with different colors. And what is interesting is that here peak of the this three jets mass is about where is the mass of top quark. It is sign that it is correct result. It must be this way. After that, to estimate to do some statistical modeling, we just use another already developed tool which named cabinetry. It is again Python library. It takes histograms from the final step. It takes some configuration file which we can write, and it do a statistical inference, and after that gives us results. And here is how the results look like after being put into a cabinetry. It returns the result of fitting, and it returns the uncertainties on the data. Well, that is last part of the of what we have if in analysis grand challenge, which is result diagnostics. But here it is. And to summarize all the project, that I just want to say that okay, as was planned in the project, the version of analysis grand challenge was implemented. That code was documented and in relatively simple language that other people can use it as an example of how to do analysis. And the code itself available in either of these two, on each of these two GitHubs. First of all, this first one is, let's say, where it was work in progress, but now it's final version. And the second one is just copy of first one, but it is on IRIS-HEP site. Okay, that is all what I want to share with you today. If you have any questions, please ask. I will be happy to answer.
Thank you, Dennis. Any questions for Dennis? Nice talk, Dennis. Thank you. Up next is Oleksii, sorry.
Hello, I'm Oleksii Hrechykha, a second-year master's student in applied physics at Kyiv Academic University. And this year I've been an IRIS-HEP fellow working under supervision of Jim Pivarsky and Jana Osborne of Princeton University. The subject of my work has been the development of ragged array library for Python. And in order for me to introduce you to what it is, I must start from afar by saying that, as we all know, Python is a quite slow language for most purposes, and because of that, specific libraries are developed and implemented by groups of people, sometimes scientists, and all of these libraries usually share some or solve some specific problems. And the more libraries there are, the more fragmented the specific libraries ecosystem may become. And because of that, some sort of standard must be introduced for the libraries to be somewhat interchangeable. As for array libraries, there is such standard. It's called Array API, and it basically governs and standardizes what a user may expect when using a certain library. So it must have constant specific functions that do the things that he can expect them to, and so on. Most libraries, most popular libraries are using some sort of standard that and you may, so things like NumPy, TensorFlow, PyTorch, Dask, etc. And to go one step back, the ragged and awkward array libraries are allowing the user to work with specific types of array. So there is an awkward array library which uses NumPy and allows for some for basically almost arbitrary data structures and almost arbitrary array the way that it looks, because this may be needed in high energy physics when some particle does not have the amount of parameters that you want it to, and other libraries are not capable of working with such data. But the problem with awkward is that it's too general and it cannot possibly work under such an array API, which is why ragged array library is developed. And this library is a wrap around awkward, which limits its functionality, but at the same time makes it API complacent. So a ragged array may look like this. So it's just an array which consists of lists of arrays of different lengths. And another difference from awkward is that it only allows for numbers to be implemented in here. So both of these array libraries are a lot faster than working with Python objects. And throughout my fellowship, I have been working on specific functions for regular libraries which exist here. So the set functions. The libraries the specific functions that I worked on are of unique branch. And as you can see here, this includes 4 functions, one of which returns the unique elements of an input array. The next one returns unique elements and their corresponding counts. And another one returns the unique elements as well as the indices of these unique elements, which allow to reconstruct the array from these indices when you put in the unique values instead of the indices. And the final function basically is a combination of those 4. And the way that it works is that I have this scripture that says taken from the Array API website, which tells me exactly what the function should do, what sort of input it takes, what is the expected output, and its data type. And the implemented function does that. Basically, the idea is to rely on NumPy and sometimes awkward functions as much as possible because they drastically speed up the computation process. And it goes for most functions that there are some input cases which we handle separately and then return, in the case of unique values function, just an array of unique values. And in case of other functions, we are returning a name tuple of certain things discussed here. And another thing that's important when writing and implementing such functions is making tests precisely for specific cases which may occur, such as an empty array, for example, which just looks like an empty list and it should be handled. However, in my case, the functions wouldn't do that, so that needed a separate condition for that. And another such instance is a scalar value. So when you have an input of regular array of just some number, floating point or integer. And I think the most tricky function by far was unique. Yeah, this one, unique inverse function, which says that you must output an array which reconstructs X, and it has not been very obvious to do. But in hindsight, the functions seem easier, I think, than what they looked like when you don't know what you are, when you have zero idea as to how to implement this. And throughout the projects, some other things appeared, such as porting the array library to NumPy 2, which arose due to an issue with some of the G-type conversion in the newest NumPy version compared to some of the oldest ones which are currently supported. And this must have been done because otherwise the CI check would fail, and some of the systems which the library must support wouldn't have been supported. And the issue was that some type changes happened in functions that return a ceiling and the floor of an of some input. And the fix was that when there is a new version of Python, it does not have explicitly numpy.array API, and the old version does, and depending on that, a certain version of a function would be run. And some other issues included basically small errors when you want to do a when you are expecting to see some sort of output, but then it returns an error because, for example, a case of some type of empty array, that wasn't handled, and with and my supervisors helped me navigate that a lot. Yes, in closing, I have enjoyed working as a fellow a lot, and the most important thing it has taught me is how to organize time and effort and see how much work you can do regularly, as well as lots of other things, such as both soft skills and hard skills, like some of the previous students have said, because it's important to ask questions, to make progress, and to communicate on the issues that you have. And also, I've learned before my project started, I don't think I have known any of the things that I've worked on here, starting from using GitHub, making pull requests, creating branches, etc. As well as it's also been my first time collaborating on someone. And now I can say that I also greatly appreciate the time and effort that it takes to create even the simplest functions, which make a small part of a certain library. And from my where is it? From my project proposal, you can see that it has a lot more optimistic timeline, and eventually all of the time that I've worked on the project have been just spent on implementing functions and tests for the unique branch of functions. And also I'd like to thank my mentors, Jana Osborne, whose assistance has been invaluable throughout all of the errors I have been encountering, and Jim Pivarski, whose reports on my pull requests and commits have been have shown many simple to overlook cases that are important for the user, and this has been the guiding force behind the eventually merged unique branch of functions. So thank you, and with that I'll be happy to take any questions.
Any questions or comments? All right. Thank you for the talk. Thank you, everybody, for coming. Thank you to the fellows for your presentations.
Thank you.
Thank you to the mentors. That's it for today. So thank you.